In this section we're looking at the complex conjugate, and we also need to understand a bit about the modulus to work through the complex conjugate. So the modulus is the absolute value or the magnitude of z, and it's essentially the distance that z is from the origin. So if we think about a complex number of the form z equals a plus bi, think about what that would look like in the complex plane. So we'll just make a and b positive here. So we've got a plus bi, which would be here. Remember, this is your imaginary and this is your real. So that's where z would be. Now if we're interested in the distance that z is from the origin, we're looking at this distance here. We can form a triangle, okay? And each part of that triangle, we've got the distance a here, the distance b here, and the distance that we're interested in here is what we call the modulus of z. And we write it as a z with the absolute sign, the absolute value signs, or two vertical lines on either side. Okay, so that's what we have in here, modulus z. Now we know from Pythagoras, if we were trying to find what modulus of z is, we know that the modulus of z squared would equal a squared plus b squared. So therefore, the modulus of z is going to be the square root of a squared plus b squared. So it's effectively, and you can write this this way as well, it's the square root of the real part of z, the number only, plus the square root, and that's squared, plus the imaginary part of z squared, and all of that taken as a square root. Okay, so that's our formula for the modulus of z, or the distance of z from the origin. So that's a really important formula for us to know. Okay, now we're going to look at something called the complex conjugate now as well, and the complex conjugate is given a special notation. So I'll just write complex conjugate. Oops. The notation that we use for this is we call the complex conjugate z bar. Okay, it's called z bar because we take z and we put a bar over the top of it. The complex conjugate, what this does is it takes the imaginary part of the complex number that you have and it changes the sign. So for our z that we have here, z equals a plus bi, we'll say that's the z that we're working with. Okay, our complex conjugate would be z bar equals a. We don't change the sign on the real part, but we change the sign on the imaginary part. Okay, so change sign of the imaginary part of z. Okay, so that's our complex conjugate. So depending on what you start with, you might be starting with a negative sign up here, then your complex conjugate would have a positive sign. Okay, the interesting thing, I guess, with the complex conjugate is this key point here, that the conjugate of z plays an important role in complex numbers. It's the only complex number which will produce a real number when it's added and multiplied with z. Okay, so if we have a look, we can try that out. Okay, so we've got z equals, again, you could do this with real numbers in here instead of a and b. I'm just using the more general a and b so that it's applicable for any case. And it's just good to get used to working with sort of more general stuff in complex. It's often what you're asked in an exam situation. So if we look at the first thing here, let's test z plus z bar. What we're going to get is z plus, let's add the z bar. And you can see immediately what's going to happen here is your a's will combine together, but your I components will cancel each other out. So you're actually going to end up with here 2a. Okay, what you can say about that then is that z plus z bar equals, now you could write that as 2a, or if you wanted to be more particular about it, you could say it's 2 times the real component of z. Remember that a is the real component of z. So it's no longer an imaginary number. So it's not an imaginary number. Oops. Okay. So the other one that we're looking at here is z bar. So it's a multiplication question. So if we have z bar, we've got z, a plus bi, and you could stop the video here and actually work through this one. See if you get the right answer. So multiplying across the brackets, so you're going to have a squared minus abi, and then the second term plus bai, and then here we've got minus b squared I squared. Now the thing to recognise here is that with complex numbers, even though you've got the a and the b around the other way here, they're exactly the same. It's like 2 times 3 is the same as 3 times 2. So these cancel out. The other thing to notice here is that you've got negative b squared, and remember that key important thing to remember is that I squared equals negative 1. Okay, you always want to keep that in the back of your head. So I squared here is negative 1, so that means that we've got a squared minus b squared times minus 1 is plus b squared. So what we actually find here, if you compare this to what we know over here about the modulus, can you see here we've got the modulus of z squared is a squared plus b squared? So that actually tells us that z bar equals the modulus of z squared. And that's an entirely real value because there are no imaginary parts to that number. So that's not imaginary either. So 2 really key points from the complex conjugate. The first thing is that the complex conjugate is the number that you get, the complex number, where you change the sign of the imaginary part only. Okay, only change the sign of the imaginary part in your complex number. That's for your complex conjugate. And 2 important results. The complex conjugate can be multiplied with the original number to give you a real number, which is the modulus of z squared, and by adding it to the original complex number, you can also eliminate the imaginary part as well. These are really useful, particularly in proofs, when you're trying to show certain results starting with complex numbers.